go. So I'm not going to talk about mesh analysis in terms of actually teaching you mesh analysis. We've done that. I'm not going to talk about nodal analysis in terms of teaching it. We've done that. What I want to do now is move on to a couple of things, and I've reorganised it a bit from the ordering that the topics are in Blackboard. Let me just remind you that let's log back in. Oops. Oh. We don't want 497, we want 236. So this is the home page called course content. You can also get there by clicking on course content. And all the slides I've been using, the PDFs are there, right? So if you need to get access to a PDF version, they're all there. You should, I believe, also know about the web work, the thing that I actually use for displaying all of this should be available to you both in the web version, so all of the scroll that I write up there is available, or if you use OneNote, you should be able to access the OneNote this notebook directly. Now you won't see all of this stuff, right? You'll probably only see like your name here, and right, so here I can distribute something specifically to each student. And the usual reason I'm going to do that is if you were asking a question via email or whatever and I wrote a note about it, I usually put the note in there. The main reason though that all of you will eventually, there's nothing here yet, but I'm going to put a copy of the midterm paper in there so that you'll see it. And again, I'll make notes on that midterm paper and you can see my notes. I just find it's a good way of sharing information. So let's just do that, because I didn't do any changes. So in fact, let me go on to oh, I forgot to add it. So we've got another lab today. I want to do the mesh and nodal analysis one. I want to talk about I want to talk about two things today. I won't talk about maximum power transfer. I'll leave that probably until next week. But I want to talk about another algorithm. Remember, mesh analysis was an algorithm, nodal analysis is an algorithm, superposition is another algorithm. It's not quite as enumerated as the other two, and maybe that's something I should do. I haven't checked Professor Broderick's latest version. But that would be a good thing, I think, to put it, write it down step by step. The other thing I wanted to talk about today is an application of nodal analysis. Right? One of the key things. So these devices are a thing called an operational amplifier. It's an integrated circuit, and as the name suggests, it lets you amplify things. So you can make the voltage bigger, you can make the current bigger. Thank you. Okay, I'll get that right here. Now, these particular ones are starting to go the way of the dodo. Right? These are nice for us. Because they plug straight into our prototyping board. If you're actually going to use one in electronics, you're probably going to use a surface mount device, which is hard to use in the lab. Anyway, the nice thing about operational amplifiers is they're real. I just gave you one, right, to have a look at. But the ideal way of looking at them works really well in real life too. And I want to talk about the ideal amplifier, ideal operational amplifier. So that's the stuff. Sorry, there's about an 8-second lag there. That's not good. Okay. So, you can see we've done a lot of stuff already. Unfortunately, or I don't know whether it's unfortunate, but these things here, mesh analysis, nodal analysis, Thevenin and Norton's theorem, take a little bit of time. It's not like Kirchhoff's voltage law or Kirchhoff's current law or Ohm's law, which are pretty easy. You've got to spend a bit of time on each of these. Mesh analysis and nodal analysis are probably the most complicated things we do. Superposition isn't that complicated, it's just another tool we can use, and Thevenin's theorem and Norton's theorem is also not that complicated. The thing that makes superposition or Thevenin and Norton complicated is they're an adjunct to mesh analysis or nodal analysis. So you've got to use mesh analysis and nodal analysis and superposition to solve problems. or you've got to use Thevenin's theorem and nodal analysis to solve problems. So it gets complicated because you have to use them together. Okay, so let's talk about operational amplifiers. So I can find the event. So excuse me, I always use the term op-amp, but the full name is operational amplifier. Okay? And as we just saw, that's what one looks like. The workhorse operational amplifier. There are others, but the one that just about everybody learns on is the 741. That's the one that I just handed out. And these are the connections. Right? You've got a power supply, right? Positive and negative values of the power supply. You've got a non-inverting input. You've got an inverting input. And you've got the output. When we draw them in a circuit diagram, we use this triangle with a positive and negative on the appropriate input and the output coming out the point, one of the points of the triangle. I'm not going to really talk about offset null. You can think that ideally what you want in an amplifier is if this is V in and this is V out, you want something like this, right? Where this is the gain. Right, the slope of that curve is the gain. The problem is in a real device, sometimes it doesn't go through zero, just out of the box. So that's what these offset nulls allow you to do. They allow you to tweak it so that it goes through zero. At least that's one way of thinking about it. But I'm only going to talk about the ideal operational amplifier. So here's a circuit. And this is the way you would connect it up. You'd have a negative supply, you'd have a positive supply, you'd have an inverting node in, you'd have a non-inverting node in, and you have an output node. And the easiest way to analyze circuits with op-amps in them is using Kirchhoff's current law. And that's why all the currents are labelled. It may be that they give an amplification in voltage, but the analysis often works on current. So these are some of the real limitations. So if you have a real op-amp, these are some of the real limitations. The first one, the output voltage is less than or equal to the saturation voltage. Right, so that's No, make it go down so I can write. And you might think about that. We've got a positive supply voltage and we've got a negative supply voltage applied to the device. And obviously the output can't go higher, at least in this circuit, can't go higher than the positive supply voltage, and it can't go lower than the negative supply voltage. And in fact, it's actually a little bit less than those numbers. So if the supply voltage is 15 volts, it's probably about 14 and a half it can get up to. Similarly, the current, the output current can't be as high as you might like. Again, this is the saturation current. Another thing that you can't do is the output voltage can't change as quickly as you'd like. So the derivative of the output voltage has to be less than SR, stands for slew rate. And if you look up a data sheet for the 741, it'll give you all these numbers. And it'll tell you how high the saturation voltage is, how high the saturation current is, and what the slew rate is. So this is what happens when we go from having a real device to deciding that we're only going to do an ideal op-amp analysis. One of the things that happens is that the input currents on both the inverting input and the non-inverting input are zero. Now in the real device they're not zero, they're small, but for our purposes they can be assumed to be zero. The other thing that doesn't seem to make sense is this one here. The input voltage on the inverting node is always equal to the voltage on the non-inverting input node. And that doesn't make a lot of sense, right? Except that it's implied because of the gain, we assume. We assume in an ideal op-amp that the voltage gain we get is infinite. So if the voltage gain is infinite, so what I mean by voltage gain, so the output voltage is equal to some value G times V2 minus V1. Right? And this here is saying, ideally we're saying that the gain is infinite. What this equation here says is if the gain is infinite and there's any difference at all between V2 and V1, then the voltage output is infinite. And that just doesn't happen. That can't happen. The only way that can't happen is if V2 is always equal to V1. Now, there's lots of ways to use these devices. The standard way is just as an inverting amplifier. And I apologise for the pixelation of that, but apparently I didn't get a very high resolution version of this. So here, the output voltage is equal to the negative of the ratio of the feedback resistor RF to R1 times the input voltage. Let's see if we can figure out how that comes about. So one thing to note is our non-inverting input is connected to ground. What does that say V minus is? Zero. This is, and again, I'm assuming it's an ideal op-amp. So if the voltage on the non-inverting input, the plus input, is zero, which is what that ground means, earth means, that means that the voltage on the inverting input is also zero. Okay, so if that's the case, we can redraw that circuit. With one caveat. Right, so that's effectively what we've got. But now let's think about, like I said, we're interested in currents. Right, so that's I in, and that's I out, even though it's going in, it's coming from the output. Remember, one of the other features of the ideal op-amp the current going into the inverting input is zero. So what does that say about I in and I out? If we apply Kirchhoff's current law to that node there, what does that say about the relationship between I? But they're equal, exactly, right? You've got, well, I don't know whether they're equal, but what we can say is, let's go with green, right? I in, and they're both going in, so plus I out equals zero. So they're going to be equal in magnitude, but one of them is the negative the other. Right? We can't have everything flowing in. If one of them's flowing in, the other one's got to be negative so that it's flowing out. Okay, so let's try and figure out on this side. So I in equals VI on R1. Right? And on this side, I out equals V out on RF. Now we can just substitute both of those in, and we get VI on R1 plus V out on RF equals 0, or VI on R1 equals minus V out on RF. Right? And if we multiply both sides by minus RF, we get V out equals minus RF on R1. And believe it or not, I've just effectively done nodal analysis, right? There's one node, and I've applied Kirchhoff's current law to this. Some of the other circuits here are more complicated, and there are more nodes, but it's still just application of either Kirchhoff's current law or nodal analysis. Now the sorts of places you use these in real life are if you've got a strain gauge, and strain gauges give you a bit of voltage but not much, and you want to amplify it. 741s themselves aren't great for audio. You can use them for audio to make pick up from a microphone louder, but they're not great. There are better. They're still op amps. There are op amps designed specifically for audio. But again, the design, the analysis is done exactly the same way. They're just a triangle with a minus input, a plus input, and an output. The real devices have those slew rates and saturation voltages and currents. The one thing that I haven't told you that I should is what G really is. And it really depends on the frequency. Right? In reality, G can be greater than 50,000. Right? So it's still pretty big. And you know, it's probably, if it's 50,000 or even if it's 10,000, that probably makes our ideal analysis only out in the third or fourth significant figure. Right? So the gain is still pretty big. As you change the frequency, so at DC it's that level, at zero frequency. At a gigahertz, it's nowhere near that. It's maybe 1, maybe 2. You can get microwave level operational amplifiers, but they're very expensive. And there's better ways to do gain in that area. Okay, that's about all I have to talk about as far as operational amplifiers are concerned. there's not much to it. The stuff you've done with mesh analysis and nodal analysis is more complicated. The three things you've got to remember are that there's no input current, that there's no difference in the voltages, and that lack of difference in the voltages is implied by infinite gain. I don't think there's much else on those. We'll talk about those. So, other things we could do with this, we could have a non-inverting amplifier, right? We don't want the output to be the negative input. So here's a non-inverting amplifier. We want a voltage, we can make a voltage follower. So the output just follows directly the input. Any idea why you might want to do that? Any thoughts? So, the problem with electronics is that they often have to connect to the real world. And the real world is dumb. So oftentimes if you've got an expensive piece of equipment, you want to somehow isolate the expensive piece of equipment image from the real world. Right? So this thing here, this, as it says, it's called a buffer. And sometimes you'll see it just done electronically using a 741. More often in industrial applications you'll see that buffer done optoelectronically. Right, so there's no electrical connection between the input and the output. And there's effectively an LED on the input side and a phototransistor on the other side. But it's set up like effectively like a buffer. A unity gain amplifier. Other things you can do? You can make a summing amplifier. Alright, if you want to add stuff up. This voltage plus this voltage plus this voltage gives some weighting on each of the inputs. This one is inverting, this one is non-inverting. Sometimes you do actually want to amplify the difference between two signals. A lot of signaling in harsh environments is done using what's called twisted pairs. Right? That's we got one here. I'm not going to unplug it from the wall, but so this stuff here, this is a type 6. That's right, one of them. But that is just a group of, I think it's 3, four twisted pairs. The reason they're twisted is if you just have something that you're measuring here, and you've got the meter over here, if you get noise on the line, then that noise shows up here. But if you do a twisted pair, and I'm not going to be able to draw it nicely, so I'm just going to draw a straight one to our meter. If you have a twisted pair here, this current is flowing this way, and this current in the other one is flowing the other way. So any noise you get tends to cancel out. Right? One of them impacts it with the current going from left to right, the other one impacts it with the current going from right to left. So instead of getting something like that, you'll still get noise, because it doesn't completely cancel out, but it's going to be much, much lower noise. So that's why you might have a differential amplifier. And there are others, I'm not going to go through them. Actually one other one I would talk about is this one. Bridge amplifiers are used because they're often used in measurements, and you can get really accurate measurements with a bridge amplifier with inaccurate values of R1, R2, R3, R4. You've seen how inaccurate our resistors are, right? They're not exactly what they tell you. So using a bridge is often a good way of nailing down accuracy. Okay, that is all I have to say about op-amps. Any questions? No? Okay. I don't yet have a lab for op-amps, so we'll see. Now that I know we have some over there, I might write up a lab. That might be good to do. So the other topic I wanted to talk about is superposition. Oh, we do have this step by step. I'd forgotten about that. So at a top level, the idea with superposition is any independent source, a voltage source or a current source, has exactly the same effect on the circuit regardless of any other independent source's effect on the circuit. So what that means is we can analyze the circuit one independent source at a time. Right? And so that's why it starts off with select each independent source. It needs to be independent. If there's a dependent source, one of those diamonds, that always stays in the circuit. If it's a battery or a round source, that's an independent source. So you select one of the independent sources, and then you replace all of the other independent sources with their ideal sources. And I'll tell you what an ideal source is shortly. Then you can just analyse the circuit using that single source and solve for whatever you need to solve for in the original problem. Then you go back and you select another one of the independent sources and you do the same thing again. Then you go back and do another one of the independent sources and you do the same thing again. Once you've iterated through all the independent sources, then the answer for the full circuit is just the sum of the answers you got for each individual one. So the tricky bit here is, what's an ideal source? And an ideal source, right, so here's a voltage source. Here's a current source. Let me see if I can so the trick with independent sources, ideal sources, is that you take the value of the source and you set it to 0. Right? So if Vs is 12 volts, you set the voltage to 0 when you replace Vs with its ideal. So let me choose someone. Marcus, any idea about what replacing Vs with its ideal might look like? No? If you set Vs to 0. No? Let's try someone else. Brianna, any thoughts? Yeah, it's just a wire. Right? So so let's walk through the logic of that. Right? If we set Vs to 0, that means that the voltage here is the same as the voltage here. Right? And remember, a node is an area of constant voltage. So that means, because they're both at the same voltage, that really it's just a wire. Okay. I think Jack is here? No? I think he's sitting there. Aretha, any idea about the ideal for the current source? No?
Would it also just be an empty wire?
An empty wire.
Just a wire with nothing on it.
A wire with
Just a wire.
just a wire? No, it's not just a wire, right? So let's think about it. We've got Is equals 0, so there's no current flowing through here. Right, so we've got basically that. It's an open circuit. Right? That's the only way you get no current flowing. Guaranteed. But there's no current. But there's an open circuit. Right, so that's the ideal for a current source. And this is the ideal voltage source. Okay, so there we go. So let me do an example. Do I have to... Right, so here's a circuit that we can, this one we could analyze just using our, well, we could probably do it using, I don't know, maybe we couldn't do it using just simple combinations of resistors in series and parallel. We could do it using mesh analysis. I think we did it using nodal analysis. But the aim is to try and find phi out. Right? So we go through each of the independent sources. There are only two sources, both of them are independent. And we replace the first source with its ideal. It was a, so we're starting off with this one. So its ideal is just a wire. Right? So that works. And then we remove the second source. And let's go back and see the second source. Right, there's our second source. And we'll replace it with its ideal. Again, it's just a wire, they're both voltage sources. Now, this one, should be easy enough to figure out. Right? We don't even need nodal or mesh. Now that we've got it like this, we can just say that we have R1 in parallel with R2, right? And that equals 5 ohms. So then what we get is, with that we get VA equals 5 on 15 times 60, right? Because we've just got a voltage divider. We've got our right, there's our 10 ohms, there's our 5 ohms, and there's our 60 volts. Right, so that's 1/3, so that's 20 volts. The current IO1, right, that's the thing we're trying to find in the original circuit, is therefore just VA on R2, right, which is 20 on 10, which is 2 ohms. So that made the circuit much easier to solve, and we have the first answer. Removing the second source, R3 in parallel with R2 is 5 ohms. Right, they're both 10 ohms. So 1 on 10 plus 1 on 10 is 5 ohms. And that makes VA equal to 5 on 5 plus 10 times 30. So this time it's 10 volts. And IO2, the thing we're trying to find in the overall problem, is VA on R2 again. Right, and then our overall answer is just the algebraic sum, which is equal to 2 plus 1, 3 amps. Okay? So here's the same circuit, but now we've got a current source and a voltage source. And again, we're trying to find the output current. So here, well, we can just look at this node. Well, we can do two things. We can look at the node and we can say that IR1 plus I out1 plus IS equals 0. They're all flowing into the node. So we just apply KCL. Another thing we can know is, and it's a bit of a short circuit for this particular one, is that if you've got two resistors and they're the same resistance, the current's going to flow through each of them equally. Right, so that means we know that I out 1 equals IR1. So 2 I out 1 equals minus IS. IS is minus 3, so I out 1 equals 1.5 amps. Now we can remove the current source, and look, it's empty. Remember, the ideal for a current source is an open circuit. What that means is that that's really the circuit we're analysing now. Right? There's zero current flowing through R3. If there's zero current flowing through R3, there's no voltage drop across R3. So we can effectively ignore it. So now the total current, which is just IO2, is going to be just that. We've got R1 in series with R2. Just add those up to get 20 ohms. The voltage drop across them is 30 volts. Apply Ohm's law. And we get IO2. So then IO2, the total IO, let's try that again. IO is just IO1 plus IO2, and I've forgotten what they were, but both 1.5, I think. Yeah, 1.5 plus 1.5 equals 3. And that's about it. There's not much to it. Again, it is algorithmic. Where it gets tricky is when there are dependent supplies, and oftentimes in the more complicated questions you can't just get away with Ohm's law or current dividers. You have to also apply mesh analysis to every circuit, right? So instead of just one application of mesh analysis, you need to apply it for each independent supply. What I suggest you do is most of the superposition questions I'm going to give you can be solved without superposition. But I'm going to ask you to specifically solve it using superposition so I can see that you understand how to solve things using superposition. What I suggest you do is you also solve it using mesh analysis or nodal analysis without superposition to check your answer. You could also possibly use LT Spice or even MATLAB if you know how to set it up in MATLAB. Okay. But I'm always a proponent of checking your answer. Checking your answer with another method. Checking your answer with a calculator, checking your answer with LT Spice, checking your answer with MATLAB. Any questions about superposition? Very quiet today. Okay. I believe I have waiting for me in the office another tutorial sheet. Just a reminder that I do want you, if I can figure out where it got to, there we go. I do want you to go into tutorials and upload your answer, worked answer to question 8 on the last tutorial. And I've forgotten when it starts and when it finishes and all that sort of stuff. Let's have a look. Yeah. Properties, I think it's properties. Right, so you should be, it started on the 27th of February. you have until March 12th to upload your solution. Once you've uploaded your solution, you'll have until March 19th to give feedback on 2 other people's solutions. Okay? I just want you to look at the way other people solve the problem. I find it illuminating myself when I see how students do stuff. The aim is that you do the 2 parts. You upload your solution and you check on 2 other students' solutions. If you do both of those, regardless of whether you got the question right or wrong, you'll get full marks. Okay? The aim is to let you see how others do it, and maybe get feedback, right? And I think I can remember where I... Is it properties? I think I've forgotten where it gets set up. No, that's the assessment canvas. Is it there? Criteria, there we go. So the things that I want you to do are basically to follow the nodal analysis algorithm. Have you identified the nodes? Are the element currents expressed as functions of the node voltage? Is KCL applied at each of the nodes in the circuit except the reference node, or node voltages are directly inferred if we get a freebie? Terms are distributed in groups and you solve it. Right? And when you grade another student's work, it's going to ask you to check off those 5 criteria. Okay? So I'll probably do another one of those on one of these on superposition as well. Okay, let's take a 10-minute break, and I'm going to go grab the tutorial and some coffee probably, and we'll talk about some other stuff when I'm done. Timing, maybe that one? Yeah, let's not go with that. Let's go with these. There we go. Grab some food. I hate that. Where's those? Go. You can open this file in another application. Okay. Try that again. There we go. Look at that. Huh. Why I think that's easier than just going insert, I do not know. But let me also set that up. So there's tutorial 3. Copy link to page. Link. Okay, so that should now also appear in Blackboard, and you have the printout. So there's 4 problems. I'm going to do what I normally do. I'm going to do one, and then I'll get each row to do one of them. One of these will be another clear review as well. Probably question 4, I think, is the one I was looking at. Is that right? Ooh, we don't want to do... Actually, I forgot about that. This has got Thevenin and Norton on it as well. So I'll do question 1, and I'll get everybody to do question 2. So let's have a look at question 1. Solve for Ix using superposition. So the first thing is understand what you're being asked. Right, there's our Ix. And it is asking explicitly to use superposition. I see it. So as soon as you see the word superposition, think independent sources. So I've got one independent source here and one independent source here. So I'm going to have to go through 2 iterations of solving this circuit. So let's do this. We'll see if I can do this. Anyway. Right, so I'm going to do the first iteration, and I'm going to keep the current source, and I'm going to replace the voltage source with its ideal. Okay, so here's my current source. I'm going to keep it. There's the outline. And I'm replacing the voltage source with its ideal. Right, so there's that's 600 microamps, that's 2200 ohms, that's 2700 ohms, that's 4700 ohms, and that one's 5600 ohms. Now notice what I've done. I've placed a short circuit across R4. So that means R4 doesn't matter. The voltage on one side of R4 is the same as the voltage on the other side of R4. So I can redraw the circuit again. And that is equivalent. Because I can basically ignore anything that's happening here. Yep. Well, I can't ignore it if, like, I couldn't ignore it here, right? But because I've put in a short circuit, this whole thing is a node. I'm going to use this whole right. This whole thing is a node. Sorry?
You have the ideal IX. You replace those to do that with the ideal source.
That's correct. Yeah, with just a short circuit with a wire. Okay? And so that makes the reference node, not the lower node, it doesn't have a, well, it did have a, sorry, I forgot to draw the earth on there. But because now the top side of the 5600 ohm resistor is connected to ground, as well as the bottom side. Nothing's happening. Huh? It's got the same voltage on one side as it does on the other. I equals V on R, V equals 0, because the voltage drop across it is 0, so it's not doing anything, so I can ignore it in any way. Does that answer the question, Mark?
Yeah.
Yeah?
Thank you.
You're welcome. Okay, so now what do we do? Well, another thing to note about this, I'm going to try and solve this in the simplest way possible. But one way I could do this is with mesh analysis, I could do with nodal analysis, but I think that might be too complicated. So I'm just going to think about it in terms of a current divider. Right? So if I have 600 milliamps going through the 2200 ohm resistor, how much current is coming out the other side of the 2200 ohm? 600. What goes in must come out, right? That's effectively what Kirchhoff's current law says. What goes in must come out. So, in fact, that's something that you really should take to heart, that if you have a device and it has X amps flowing in that side and there's no other connections, it has to have X amps flowing out the other side. Okay, so now we've got 600 microamps flowing into, so I can actually redraw this what was that? That was R2, I think. Yeah, IR2. So I can redraw it again. And I apologise for my scrawl. I really should learn to write a bit better. Here we go. So now we've got a current divider, or we could apply Kirchhoff's current law. Let's just get the numbers on there again. So this one is a 4700 ohm, and this one is a 2700 ohm. Try to remember to put the units there. So remember, with current dividers, the current in the branch we're interested in is proportional to the resistance in the other branch divided by the total resistance. And in this case it's simple, the other branch, there is only one other branch. If there were more than one other branch, you'd have to lump the other resistances together in parallel in order to know what the other resistance branch was. The thing that's a bit different about this one is the direction of the currents. Normally, if I think about current dividers, I have them defined like that. Right? But now I've got, because of the direction Ix was defined in, I'm going to have a minus sign in there somewhere. But that's okay. One way to get around that is to know that Ix plus IR2 equals 600 microns. Right? That's Kirchhoff's current law. What goes in must come out. So Ix now remember, this is the first one. We've removed Vs. So I'm going to call it Ix1. Right, because remember we're going to have to solve it again for replacing the other source. Okay, so Ix1 equals, now the resistance in the other branch is 4700, so the total resistance is 4700 plus 2700. Now it's going to be times minus 600. And let's just see what that gives us. I'm just going to use my simple calculator here. We'll clear 4700 divided by, what's that? That's 7400, I think. Times right, so it's minus 381.1. Okay, so we've solved this circuit by keeping Is and replacing Vs. Now we're going to do the same thing again, but this time we're going to replace Is and keep Vs. Oops. Okay, I replaced the current source with its ideal, set the current to 0. Setting the current to 0 makes it an open circuit. And then I can just leave it open. This one here doesn't take any part in the analysis. Right? There's no current flowing through it. So I can just redraw the circuit as, let's center it on the 10 volts. And I forgot to write in IX again, so there's our IX2. So now it should be pretty simple, right? We've got a, what's that? That's 7400. So it's going to be, another way to redraw this is right, where this is the 2700, that's the 4700, that's the 5600, and that's our IX. So this whole thing here is going to be 5600 in parallel with 7400. Right, which is our one on 5600 plus one on 7400. And I don't know, oops, not 74,000, let's try that again. See if I can do that. I might have to switch to the scientific version. Right, so 1 divided by 5600 and 1 divided by 7400. And then none on X, right, which is 3188, I think. Sounds about right. And what's that, IX2? So that's 3.137 milliamps. Right, so then our total oops. I don't know how that happened. Try that again. Our total is just our minus 381.1 by 10 to the minus 6 and 3.137 by 10 to the minus 3. And I don't know if I can do that. So minus 381.1 Eek. That didn't do it. I might have to do that one in up here somewhere. So So minus 381.1 by 10 to the minus 6 plus 3.137 plus 3.137 by 10 to the minus 3. Right? I did get it right. Just didn't show it to me the way I expected it to. So it's 2.756. And you can either write it down as 2.756 by 10 to the minus 3 amps or 2.756 milliamps. Everybody okay with that? Okay, I suggest you all try and do problem 2. Feel free to work with your neighbours if you want to, and I'll come back in about 10 minutes and see if we can work through it together. Are there any leftover tutorials? So does anybody have a diagram for the first step that I could take a picture of and we just see it? So somebody's a little diagram happy enough to go? This one? Okay. Thinking about it. There we go. Now let's see if I can open up this. That one. There. Here's what it is. Okay, so here's the first look at it. Right, we've got keeping the voltage source and replacing the current source with its ideal, which is an open circuit, and therefore we can scratch anything to do with R1. Anybody got the other circuit? I can take a picture. The other circuit? Insert that one. Hopefully that'll come in short. Maybe if I keep that one running. There we go. Okay, so let's just move it over here so we can see everything on the screen at once. Right, so here's the other one. We've replaced the voltage source with its ideal, and it's just a wire, and I think that also means, I didn't take a picture of the next one over, but I think that means R4 is just shorted out. So just like R1 in the first instance, and I should stop using black. Apparently it shows up as white. I should figure out. So basically we should be able to ignore R4 in the analysis because it's shorted out. I'm just going to write IX1, and I'm going to call it IX2. I think that was your first one, but I second that. That's okay. So let's focus on this. What happened there? Let's focus on this one first. How did we solve this one? Rihanna, how did we solve it? Exactly. This one it's pretty simple, so that would be a perfectly valid way to do it. We could also do, let me try different colours. We could also do a mesh analysis, and solve I1 and I2, but that might be overkill for this. I usually like solving things in the simplest way possible, and in this case, just doing the equivalent resistance approach is probably the simplest. Okay. So how about this one? Let's see if I can pull up someone random. Where's Kevin? Kevin here? Maybe not. No? Nicholas, what did we do here?
First is like the last problem of current on the same
Right, so we've just got IS coming through here, right? Right, I think the resistance values change, but the approach is exactly the same. Yeah, exactly.
What is that thing?
Which the right, so when you've got a, and that's why I this is the thing I drew out, right? So here's I in, and normally the output current is flowing in the same direction. So when you've got a situation like that, that's a current divider. You've got one current flowing in, and then two or more paths that it can flow through. So in this case, I out is proportional to the resistance in the other path. So it's R1 divided by R1 plus R2 times I in. Okay? Now, it gets more complicated when you've got more resistors. Right, so suppose that's R1 and this is Rn, N minus 1, N minus 2. Here, the resistance in the other path is the equivalent resistance of all the other parallel resistors. Right, so it's going to be Rn in parallel with Rn minus 1, in parallel with Rn minus 2, all the way down to in parallel with R2, divided by R1 plus the same thing again, Rn in parallel with Rn minus 1, in parallel with Rn minus 2, in parallel with R2 again. So it's easy or easier when there's just two resistors. But when there are multiple other paths to deal with, you have to figure out what the resistance of that other path is. Does that answer the question? Yeah. Okay, so I thought it might be either entertaining or scary, maybe both, to have a look at a past final exam let's go with that one, because we all know what's on the midterm, right? Superposition is not on the midterm. Right, so here is the final from last summer. And this is the format that you should expect on your final. It's not necessarily going to be the same circuits, but similar format. Notice the level of complexity has gone up, right? It's not just about superposition. It's also you bringing in the stuff we're going to do next. Resistors, capacitors and inductors in the same circuit. But the idea is pretty much the same. Here we've got a voltage source and a current source. We replace the voltage source and analyze just with the current source. We replace the current source and analyze with just the voltage source. And it all just works the way you would expect. Here's another one. Slightly different. Here's another one. Again, slightly different. There's a more complicated one again. what I'm going to do in the final is for each topic, I'm going to give you 3 or 4 circuits. When we come to the actual final, I'll ask you to explain how you will solve one of them, and then get you to just explain the process, not the detail, while we're on the call. And then I'll get you to upload your solution, or do your solution in Inverting. Okay? So you will have to solve things numerically. You'll have to do it in a short amount of time, but not too short. But the main thing to do on the call, when I talk to you, is explain process. If you I'm looking that you understand the steps you have to approach in measure analysis or nodal analysis or superposition. If you know what Ohm's law is, if you know what KCL is, if you know what KVL is, that sort of stuff. Okay, I'm not going to go through the full solution. I'm going to put this question up as another peer review. It won't open until after the current peer review closes, so I don't like necessarily burden you with too much work. But keep your solution for this that you've done now, and be ready to upload it once the other peer review one opens. Any questions about superposition? Okay, let's talk about the lab. Can I remember where I put it? Now, I just realised we might have a problem with the lab. Because I'm not sure putting up. How do you do it? Okay. So the objectives are to study mesh analysis and its use in multi-source DC circuits, and study nodal analysis. And then I want you to apply mesh and nodal, finding currents and voltages. So for this lab, it's a little bit more complicated than before, only in that we've got now 2 voltage sources. Right, so remember, turn one of them on and show you the picture. Oh well. See if one of these is turned on. So remember, power source, 1 power voltage, 2 power voltage, channel 1, channel 2. You can change the voltages to channel 1 and channel 2 independently, and that's what you're going to have to do here. Previously you just used channel 1. I'd suggest using channel 1 for V1 and channel 2 for V2. Channel 1 is the second pair, channel 2 is the third pair. And then what you need to do in the lab is let's go with this one. Measure these voltages. Right, so you need to measure VA, VB, and VC. You need to measure R1, R2, and R3. You'll know what their nominal values are, but they're not going to be exactly right. You've effectively got to measure V1 and V2, right? But V1 is the same as VA and V2 is the same as VC. And then the other thing you've got to do is measure the current. That should be a 1. And then what I want to see in your report is analysing this circuit using mesh analysis and get all of those values using mesh analysis. Analyse the circuit using nodal analysis. Get all of those values using nodal analysis. Obviously R1, R2, R3 you won't get, but you'll get the voltages and the current. So let's quickly do mesh analysis. Right, so there's I2, that's I1. So KVL for I1 is V2 minus V1 plus VR1 plus VR2 equals 0. So I can, I'm just going to leave V2 and V1 as they are. VR1 is I1 R1. VR2 is R2 times I1 minus I2. That equals 0. And then KVL, it's change colour. KVL for I2. We get minus V2. And this time we're going that way, so our polarities are like that. Minus V2 plus VR2 plus VR3 equals 0. And again, I'm going to keep V2. And then VR2 is R2 times I2 minus I1. And R3 is just I2 times R3. So that gives me, what's that, R1 plus R2 times I1 minus R2 and minus R2 and R2 plus R3. And on the other side it's V1 minus V2 and just V2. So depending on your R1 and R2, your V1 and V2, you can solve for what I1 and I2 is. So the only tricky one out of all of these is going to be VB. Right? That's the voltage up here. And you could get that a number of ways. I think the easiest way to get it is to just say VB is really equal to VR3. Oops. Just show you why I did that. I'm obviously hitting something. So VB is really VR3, which is equal to R3 times I2. So let's have a look at nodal analysis, right? Identify the nodes. We've got two freebies. VA equals V1. VC equals V2. And then KCL at B. Maybe let's do IR1 is VA minus VB on R1. IR2 is VC minus VB on R2 because of the direction I've chosen, and IR3 is just 0 minus VB. So KCL at B, we have IR1 plus IR2 plus IR3 equals 0, and then I can just say VA minus VB on R1 plus VC minus VB on R2 minus VB on R3 equals 0. The only unknown thing is VB. I already know what VA and VC are because they were freebies in nodal analysis. So I just have to, I don't even have to do a matrix equation in this question. I just have to plug in VA and VC and then solve for VB. Remember to go back, because remember we want to calculate IR1, IR2, IR3, VA, VB, VC, I think that's about it, using mesh analysis and nodal analysis. So the numbers you get for both of them should be pretty close, and they also, those should be exact, the actual calculations your measurements should be pretty close. Probably within 5%, hopefully within 1%. Provided you've measured the resistances carefully. Yeah?
So for the lab report, do you want us to do the work out and scan it in for the lab?
Yes, please. Yeah, that's easy. So you should be able to. Right, you should be able to. Yeah. I'm just going to do a new blank worksheet. You should just be able to go, right, insert, and somewhere there should, illustrations, pictures, there we go, from this device, and then I'm going to go to pictures, yeah. Right, and you should be able to insert it there quite happily. Don't worry too much about how Blackboard splits up the paging. That's okay. Please use either XLS or XLSX format. That way I can see it in the browser and I'm used to scrolling to get the other pages. Did you have a question?
Yeah, are you going to upload the lab itself to Blackboard?
Not on there? Oh, it's probably there. I probably just didn't. It's probably got last semester's dates, which I probably should have checked before I did it. Sorry about that. Yes, item is hidden from students. It was last available then. Let me make you actually able to submit it. Thank you. So the due date, that's the 12th. What's today? The 5th? Let's push it out for a week. And then the problem is it had that one, which was wrong. So, yeah, I think they're all the same. I'll go through them later rather than waste your time. Me show you how to navigate Blackboard. But that should show you Lab 5 now. Any questions about Lab 5? I'm going to go get some resistors. I'll get maybe 5 different values. You just choose 3 of them. And try and choose 3 different ones. And get the measurements. You don't have to solve the circuit today, but try and get the measurements today. Okay? One mystery number and 4 others. Okay, I think I'm going to turn the record